Hey, what's up, guys? Welcome to my YouTube channel. My name is Gautam, and today I want to talk about one of the Leetcode problems that I solved very recently. I had a lot of fun solving this problem. I want to walk you through the thought process behind solving this problem and the approach to solving this problem. So let's dive in. So this problem is called minimize the maximum adjacent element difference. So read through the problem quickly. You are given an array of integer nums. Some values in nums are missing and are denoted by -1. You can choose a pair of positive integers x, comma y exactly once and replace each missing element with either x or y. You need to minimize the maximum absolute difference between adjacent elements of nums after replacement. Return the maximum possible difference. Now, if you're reading this problem for the first time, I would recommend you to walk through the problem once and try to understand the problem and some use cases provided here before we dive in. We are given some examples here. So we have nums equal to 1, 2, -1, 10, and 8. Output is 4. Let's look at y. 6 and 7 is the chosen pair in this case. So if we replace -1 with, so we can remember we can replace either with 6 or with 7. So if we replace it with 6, then we get a difference of 6 minus 2 is equal to 4. 10 minus 6 is also equal to 4. And that seems to be the maximum difference. Now if you see here 1 minus 2, 2 minus 1 rather would give you 1. 10 minus 8 would give you 2. If you put any other number here, let's say 7, then the difference between 7 and 2 is 5. So that's exceeding 4. So this is the minimum. This is the minimum possible max absolute difference between adjacent elements. So in order to understand this problem in detail, let's start with a very simple use case and try to build a much more complicated use case and see how we go about it. So let's start with a very simple use case. Let's say we have something like 2, -1, and 16. And in this case, what we could do is we can expand these numbers 2 and 16. Between 2 and 16, we have 2, 3 up to 16. And then we can see number 9 is somewhere around about in middle between 2 and 16. Sorry, number 9 is somewhere around about between 2 and 16. And the difference between the largest number and the smallest number in this case is 7. So if you move to 10, for example, it will increase the difference between 2 and 10, makes it 8. So this is the ideal number. It's always in between. So if you want to like calculate with a simple formula, it's quite easy. We can see that 16 minus 2 divided by 2 gives us 7, and d is equal to 7 in this case. X, so one of the number that we have calculated is actually 9, which is 2 plus 7, 2 being the minimum value. We just add 7 to it, and then I added now a few more elements to this array just to complicate the use case and see what happens. So we know that from the previous example, d was equal to 7 and x was equal to 9. And if we add any more elements to this array, the answer could not be lesser than 7. It could only increase more. It can be more than 7, but it couldn't be less than 7 because the value between the adjacent element difference between 2, -1, and 16 kind of influences, and this seems to be at least the minimum possible value that we can get. So the idea behind that is let's try to fit in 9 in all the possible -1s that we have. So if we attempt to do something like this, we can see that, okay, 9 satisfies lesser is equal to lesser or equal to d in the pair between 2 and 16. 9 can also satisfy between 12 and 4. You can notice that, here the value is the minimum difference is 5 and 3. And if you put in 9 here, for example, 16 minus 9 is 7, and 9 minus 5 is 4. So far so good. We have uh, put 9 in three different places, and the minimum absolute difference between the adjacent elements doesn't seem to exceed d. So it has worked so far until here. What happens for the next two pairs? Here, if we add 9, then we would end up 18 minus 9, which gives us 9. 32 minus 9 gives us 23. That exceeds D in this case. D is 7. So it exceeds D. So finally, we have to now find out what is Y. So, what we have noticed is that, okay, if we have D, if we try to fit in D for all the possible pairs, we can take 32 minus D gives us 25, and we can quickly observe that 25 actually kind of satisfies this condition of lesser or equal to 9. So we can put 25 in between 19 and 32, 25 again in between 19 and 18, and you can see here the difference between adjacent pair of elements remains lesser or equal to 7. It doesn't exceed 7. One thing that we have observed here is that minimum and maximum seem to play a key role. So let's highlight this. Minimum in this case is 2, and maximum in this case is 32, because when we have a D, we always try to find maximum minus D, and we always do minimum plus D. So minimum and maximum seems to play a key role in this case. So what happens when we add one additional number, say 45? How would this affect? So we can quickly notice that if you add 45, neither x or y fits in. If you try to add y here, in this case it's 25. So we can quickly notice that difference between 45 and 25 is 20. It exceeds d. D was 7 in this case. So it doesn't fit in, neither does x. If you put in x equal to 9 in this place of 25, the difference is even higher. So now we are kind of back to square one. What is x, y, and d? But we know one thing, that's minimum is 2 and max equal to 45. So, in order to continue how to find x and y, let's imagine a number line. Let's imagine a number line, and I want to pick each one of this pair. I call this a pair because any enclosing numbers which are enclosing minus ones, I call this a pair. And I pick the left element and the right element from this pair, and I drop it down to the number line. So in this number line, you can see all the pairs which are enclosing minus 1. So now we have 9 here, but it was actually minus 1. So let me add all of this into the number line. So if I add, this is what the number line looks like so far, starting with 2 until 45. So in the previous step, we found out that x equal to 9 and y equal to 25 doesn't seem to fit in. So where does it fall in this number line? We can quickly notice that, x equal to 9 and y equal to 25, somewhere around here. And the difference between the minimum up to x is 7, and max to y is 7 again. So it seems to work so far until 32. But what happens to 45? We can quickly see that it is actually satisfying lesser or equal to d, where d is equal to 7. All these numbers are closer to y, and all these set of numbers are closer to x. 45 in this case is actually quite far away. It exceeds d. We saw in the previous step it's actually 20. Now I can't stop imagining one close to real-time scenario when I see this picture. This is what I can imagine. Imagine you're in a street with houses, and you have two street lamps, and each of the street lamps is covering some set of houses. Let's see, this first three houses are actually covered by this street lamp. The next three is actually covered by another street lamp. let's say there is another house quite far away in the street, which is not receiving any light from the street lamp. So now, given a problem that how do we make sure that all the houses along this street gets equal share or at least some share of light? We can say that okay, we could install another lamp here, and that could solve the problem. Yes, that could. But what if we have to say that we have to do it with only two lamps? So we have the problem something like this. We have X and Y. These are the points. Let's say this street is actually some sort of a number line, and we have X and Y along this number line, and we call this, let's say, a D, which is like the focus light or width of this light. Um, so if we have to fit in all the houses, and if we have to make this light like available for all the houses, we have to make something like this. We have to broaden the light range, and also we have to bring X and Y somewhere around about the mid along this line so that all the houses get some light. So this is something that I could actually relate to in the real life scenario when I saw this numbers in form of a number line. So, we found that we have to move the light point somewhere around about the mid of the number line. So let's try to do the same in this case. So we have here number line. I want to move the point X and Y somewhere around about the mid. When I move into around about the midpoint of the number line, my D increases. When I move it to, let's say here, D is equal to 18. So the X point is lying somewhere around here, 20. That's because 2 plus 18 is 20. And maximum number 45 minus 18 is 27. So X and Y lies somewhere around about here. So we can quickly check by putting in 20 here. The minimum difference is now 18. It doesn't seem to exceed 18. It's either lesser or equal to 18. And likewise here, if you add 27, 45 minus 27 and 19 minus 27 is lesser or equal to 18. So we have actually found a solution to this by moving X and Y point somewhere around about the mid of the number line, although D is equal to 18 may not be really an optimal answer. So what we did is we checked D is equal to 7 doesn't seem to work for all the minus ones, but D is equal to 18 seems to work in this case. So time to be a bit more greedy and try somewhere around about D is equal to 7 and 18. So this is where binary search comes into picture. So if we do a binary search for a number between 7 and 18, we can quickly check the optimal answer for this is actually t is equal to 13, where x equal to 15 and y is equal to 27. And that seems to work correctly for this use case. And that is the answer for this use case. So, having said that, we have a few edge cases which we shouldn't forget. So, one of this edge cases is something like this. So, in this case, we might actually figure out that, okay, we have minus one, and we have two numbers, 2 and 16, which is enclosing this minus one, and the answer is 7. But we are actually wrong. In this case, we have already an adjacent element here, 116. 100 minus 16 is 84. We have something like a current max, which is 84. So answer is in this case 84 because 84 exceeds 7 and 7 is not. So we have to always calculate something which is like a current max. Even though you might come up with optimal D, that may be smaller than already existing current max. So we have another edge case, something like this, -1, -116. In this case, what are the two enclosing numbers? In this case, we can just simply replace 16 as the enclosing number on either side. That's because if it begins with -1, we can simply do this, and the adjacent element difference, it can just remain the same on either side. So we might actually come up with an answer like d is equal to 4, x is equal to 6, and y is equal to 20. We can quickly verify that x minus 2 is actually 4, and 20 minus 16 is actually 4. But wait a minute, we didn't really check x minus y because these two are now neighbors, and the adjacent element difference would be actually 14, which exceeds 4. So we have to watch out for this kind of use cases where x and y can actually be adjacent elements. So if we implement the solution in this approach, the time complexity of this problem could be n log k, where k is the max number in the array, and n is number of elements in the given array. Space complexity is linear because we have to use some kind of an array here to keep track of all the numbers. So at this moment, maybe you can pause the video, and if you have some experience writing some code, I'm quite sure if you understood this problem correctly, you can implement this on your own. So what's the algorithm that looks like for this problem? So I have described a very simple set of steps to implement this solution. So let's start with the first one. If the array contains only -1, simply return 0. It's the easiest of use case. We can also see in the sample test case given for this problem. Calculate current max. That's the existing max that we have for a given set of array element. Now we shouldn't forget about this. We saw this in the edge case. We have to calculate the minimum and max from the array, and find d by doing a binary search. We saw why binary search is important to maintain the time complexity, and also so calculate x equal to min plus d and y is equal to max minus d. So these two numbers can be easily calculated if you have d. So now once we have x and y, we have to check if replacing -1 with either x or y, the adjacent element difference doesn't exceed d. It should always remain lesser or equal to d. So what if it exceeds? We already saw how we have to move our numbers more to the right of the number line. That means increasing d. So that means we have to search in the upper bound between d and the high. And what if it satisfies the condition lesser or equal to d? In this case, we save this as a potential answer and then binary search for the lower bound. Remember, we want to be greedy and try to get the optimal answer for this problem. So in the lower bound between low and d minus 1. Finally, when we have an optimal d, we can return answer, maximum of answer, and current max. We shouldn't forget current max because sometimes current max can be higher than the answer that we have got. Hope you enjoyed this video. If you have any comments, please feel free to drop in your comments in the comment section below. And in the description, I'm going to leave a link to my code and the Leetcode solution. Please don't forget to subscribe and like my video. See you soon.